Okay, good morning everyone. So we have sort of covered about 5 lectures. So far we have been addressing data analysis and to little extent scalable data analysis. From today we are going to start on graph mining. And we are going to continue graph mining and scalable graph mining along with a bunch of case studies and demos we have developed for this purpose. So, since I was not sure the composition of the audience, I have not made any assumptions on how much you know about graph theory. So I'm starting from basics. I hope that will help you understand and come up to speed. So this is why we need graphs for data analysis. So far we have been using relational representations, tabular representations and various data structures for analysis. But today, with the advent of internet and social networks and other things, graph representation has become very important. And graphs are very good at representing relationships, which relational models cannot do. I'll give you some examples of that later. So this brings us to the need for graph mining or graph analysis. So before we can do the graph analysis, we first need to understand what graphs are. What are the important characteristics of the graphs, what are the properties of the graphs, and what kind of computations on graphs are useful for our data analysis. So we have been using association, rule mining, decision trees and others as we discussed yesterday. Most of these are considered transactional data. That means data that are in the tabular format, that have mostly depend upon numbers, integers, categorical attributes and so on. Do not make use of any structural relationship. That means relationships between entities. So graph-based mining techniques are used for mining data that are structural in nature. For example, if you want to represent chemical compounds, it's very difficult to do it using a tabular representation. You can do it, but that's not ideal. Same thing for proteins, VLSI circuit boards, social network, as mapping them to other representations is not possible or will lead to loss of structural information. So this is important to understand why we need different models for different types of data. So one model is not going to cut out for every application. So this brings us to the basics of graph theory, what we want to do. So I usually start with this example. I don't know how many of you are familiar with it or heard of it. So there was a problem that is called the 7 bridges of Königsberg. Now it's a real town in Russia, known as Kaliningrad. It's a historically notable problem in mathematics or graph theory. This came about around 1736. You can see that it's almost 500 years ago, or more than 500. So graph theory has been around for more than 500 years. So we are not reinventing graph theory at all. We are just trying to make it computationally effective, develop algorithms for that, but there has been a lot of work, a lot of theories, a lot of properties. So there was a negative proof or resolution by this guy, Leonhard Euler, in 1736 that laid the foundation of graph theory and topology. This was a real world problem, was solved using a mathematical tool. So this is important to understand. This is a real world problem, and how do you solve it? First you have to model it in some way so that you can apply techniques for solving it in some way. So in this case, graph theory and topology was used. So what was the problem? So here is the problem. This is the city of Königsberg, and this city had these two branches of the rivers, and it was flowing like this. This is an actual picture of that, and there were 1, 2, 3, 4, 5, 6, 7 bridges across these rivers. So the question that was asked is it possible to take a walk through a town in such a way that each bridge would be crossed exactly once? That means you should be able to visit all parts of the town, this one, this one, this one, this one, crossing the bridge only once. Now, how do you solve this problem? It took almost 150 years to solve this problem. Okay, so also illustrate the importance of modeling. So if you look at it this way, you just don't know where to start. You just don't know how to go about solving this problem. You understand the problem, but it's very difficult to solve it. So in 1736, this Swiss mathematician presented a solution to this problem, concluding that such a walk was impossible. It is impossible to take that walk with the condition that every bridge is crossed only once. It took 150 years for mathematicians to formulate it as a graph problem and establish its correctness, or prove that that is the case. So here is the problem, real world problem. Here is the graph representation. So each region, A, B, C, D, is represented as a node. Each bridge connecting the regions is represented as an edge. Now you have a graph. Now you can use this graph and its properties to determine whether this problem can be solved or not. So that's how they went about modeling a real world application or a real world problem into a appropriate model, whether it's a graph or table or some kind of a dictionary or a tree, doesn't matter. So what was the solution? So there is something called this is the guy who came up with the solution, and it is named a Eulerian path, traverses each edge exactly only once. Generalization of Euler's equation that a graph possessing such a path has at most two vertices of odd degree was the first theorem in graph theory. So here is a example, but this violates, because this bridge is traversed twice. This is traversed twice, and if you look at this theorem, it says you can have at most two vertices with odd degree. Now you have this vertex with odd degree, degree 3. You have this with degree 3, this with degree 3, and this with degree 5. So it is not possible in this graph to traverse, to make a path without going through the same node twice, which means without going through the same bridge twice. So you can see how real world problems are solved using a mathematical model and then applying appropriate algorithms. So here a path, finding a path in a graph is an algorithm. It is not trivial. If you have a very large complex graph, finding a graph satisfying certain constraints is even more difficult. So this is known as the Euler path. So this is how it was solved 500 years ago, and we are still doing the same thing today. On a larger problem with more data, our graphs are millions of nodes and multi-million edges. We'll see that later, not 7 nodes or 4 nodes and 7 edges. So this itself took 150 years. So you can appreciate how it is done. So much of the data is structural in nature or is composed of parts and relationship between parts. So you have entities. So perhaps an example your Gen Z can understand is friendship relationship in a Facebook. So what is a friendship relationship? Between two people. So that's two people are the entities or the nodes, and the friendship relationship is the edge. Maybe that makes it much more clearer to you. Most of the existing data analysis mining algorithms are based upon transactional representation or tabular representation. Scientific data sets with structures, layers, hierarchy, or geometry often do not fit well in this transaction setting, protein structures, chemical compounds. Therefore, we need algorithms that take into account the structural relationships. So here are some examples of graphs or things that can be modeled as graphs from the real world domain. So this is a protein. You can see that this protein has nodes and edges. Here is a benzene structure. This benzene structure has nodes and edges. So you cannot represent it as a table in a very easy way, or even if you represent it, it's very difficult to understand it. So here is the protein represented using a graph. So to determine which amino acid chain dominates in a particular protein. So this is important. So in all these biological applications or chemical applications, the structures seem to be repeated. Even in a benzene, you can see that some structure is repeated again and again. That repetition means something. I don't know whether you have paid attention when you go and buy a drug, you get a pamphlet in that drug box which is very in small letters. In that, if you open it, you will see a complex formulation of the drug, which is actually a drug formulation, which is a graph, which looks like that, which is much more complicated. Next time when you go and buy a drug, pay attention to that. So, if you are convinced that we need graphs for modeling because a lot of real world applications need graphs to model them, then we need to understand what is graph analysis and why do we want to do that. So graph analysis, also called network analysis, so graphs, networks, monoplexes are all the same terminology for graphs, is the analysis of graphs with entities as nodes and relationships as edges. So Facebook is a good example for you. LinkedIn is a good example for you for connected relationship. Twitter is a good example for you for follows followed by relationship. They're all graphs. So Twitter is actually represented as a graph and analysis is made on graphs. Otherwise, it's very difficult to do the analysis. So you may want to find shortest path. You may want to find minimum spanning tree. You may want to find a Hamiltonian cycle or Eulerian path. You may want to search for triangles, cliques, exact and inexact substructures. So these are some of the algorithms. In addition, you may want to search for communities. You may want to search for substructures. You may want to search for centrality, nodes. You may want to consider bipartite graphs, max flow pairs. There is a lot of work in max flow pairs for in the area of electrical engineering and others. So somebody has to come up and develop these algorithms, and somebody has to use those algorithms. So that's the basis of data analysis. So unless you know what algorithms are available and which algorithm is appropriate for what purpose, you cannot become a good data analyst. Otherwise, you will just randomly apply what you know and not what is needed. So the approach is to identify an appropriate graph representation for the real world problem, identify the solution in terms of graph property or computation. So here are some examples. Most of you have heard of the traveling salesman problem. Have you heard of traveling salesman problem? So do you know how complex it is to solve that? It's an NP-complete problem. So you use dynamic programming techniques or heuristics or approximations for solving that. So this problem, for those who do not know, so here is a traveling salesperson. His job is to sell whatever he is selling, drugs or some other items, and he has to visit 10 cities and make sales. So now the question is, in what order should he visit these cities? Which order will be the lowest cost in terms of travel? Of course, you can randomly choose one city, randomly go to the next city, go to the third city, then the cost is very high and the cost cuts into your profit. So the optimization problem is find the lowest cost or the shortest distance route among the cities that he has to travel and sell his stuff. Now, if you have 1 or 2 or 3 or 5 cities, it's very easy to do that. You can manually do that. So this is the small data analysis manually with intuition. But what if you have 100 cities? And then you may not have connectivity between all cities. There may not be roads between every city, right? Then you have to draw the edges depending upon connectivity. And then you have to analyze this 100 node and maybe 600 edge graph to figure out the lowest cost route. And in that you want to visit each city only once. You don't want to be visiting the same city more than once, right? So that is the problem. But what if you have 50,000 nodes? That is the scalability issue. 5 nodes, 100 nodes, 50,000 nodes. So these are the ways we look at. So till now, mathematicians were solving the 5-10 node problem because it can be done very easily by humans and intuition, and based upon that they developed a bunch of theorems. They developed a bunch of properties, but computation was difficult. So if they changed it to 50 node problem, manual computation was very difficult. That is where automated and computer algorithms come into picture. The algorithm was there, but applying the algorithm for 100 node problem was not easy because the number of steps are very large, but computers can do it very nicely. So that is why if you have a shortest path algorithm for a graph, then you can apply it for 50 nodes. Let us say it will take 5 minutes. If you run it on 50,000 nodes, it may take 1 hour. If you don't want it to take 1 hour, then you have to worry about scalability, distributed and parallel processing. So that's what will come to that. So understand the differences between different types of this. There is also the Hamiltonian path cycle, which is also NP complete. Eulerian cycle, which is in linear time. PageRank algorithm. How many of you are familiar with PageRank? Or at least heard of PageRank? You haven't? How many of you use Google? Almost everyone, right? You use Google, but you don't know what PageRank is. That's really sad. Because what Google uses underneath to give you the answer you look for so much is PageRank algorithm. So the bread and butter of Chrome is PageRank algorithm. And that algorithm is not very straightforward. It's a graph algorithm. So think of a graph where every web page is a node. So how many nodes do you think you have? Billions? And think of any reference to any other page, a URL from that page to another page as an edge. How many edges do you think you have? 5 billion into at least 3 or 4 per page? 20 billion edges. Now you have to compute the page rank on a graph with 5 billion nodes and 20 billion edges. Think of the complexity and difficulty, but you get an answer within a second, right? And you are very happy about it, right? But you don't want to understand what goes on behind it. So, what is a graph? So we have understood what a graph is informally, but mathematicians are not happy with informal things. They want very precise definitions of everything because they want to prove things, not just approximately say something. So that's very important to understand. In mathematics, graph theory is the study of graphs, which are mathematical structures used to model pairwise relationships between objects. Pairwise means these relations are between two objects. So certainly, Facebook friendship fits it very well. LinkedIn fits it very well. Twitter also fits it very well. But there is also something called, you can have more than two, which is known as the hyper edge and hypergraph. We will not discuss that. A graph in this context is made up of vertices, also called nodes or points, which are connected by edges, also called links or lines. A distinction is made between undirected graphs, where edge links two vertices symmetrically, and directed graphs where edge links two vertices asymmetrically. So, when you have an edge, it can be a bidirectional edge or it can be unidirectional edge. In some situations, so for example, when you say greater than as a relationship, 100 is greater than 50. Then you draw an arrow from 100 to 50, but then you have to put a direction, right? 100 is greater than 50, but 50 is not greater than 100. You cannot draw the other edge. So it is not that always you will have both edges. In many cases, the edges are one way, but in many cases, the edges can be both way. In a friendship relation, if A is a friend of B, the assumption is B is also a friend of B. Otherwise, it will be a one-sided relationship. A likes B, but B doesn't like it. That happens a lot on Tinder, but in graphs, it's very different. Okay? So graphs are one of the principal objects of study in discrete mathematics. I'm sure you have studied discrete mathematics in your undergraduates, but I don't know how much of that you remember. So let's try to understand a little bit more of the graph. So a graph is an ordered pair G consisting of two sets, V and E. Set of vertices, set of edges. Also, E is a proper subset of xy, where xy belong to V and x is not equal to y. This is an undirected simple graph. So why do we have the condition x is not equal to y? What happens if x is equal to y? Huh?
Straight line.
Can you, I can't hear you, can you?
Straight line graph.
Huh?
When x is equal to y, the straight line graph forms.
Okay, can somebody repeat it? I mean, what happens if x is equal to y? What kind of graph do you get?
Straight line.
Huh?
Straight line. People are saying that there would be a straight line graph would form if x is equal to y.
No, not straight line, not good. You get a loop. If x equal to y and there is an edge, The edge is that edge to itself. So that is a loop. So in a simple graph, loops are not allowed. Cycles are there. Cycle is not the issue. You can have x to y, y to z, z to a, z to x. So cycles are not the problem, loops. If x is equal to y, then you can have a loop in the graph. Otherwise, you cannot have a loop in the graph. So understand the definition clearly. So here is a 3-node graph. This has 3 nodes and 3 edges. This has an importance. This has a significance in graph theory and in real life. And this kind of graph is called a clique. I don't know how many of you are familiar with cliques. You may be familiar with social circle cliques. You know, this person belongs to this clique, this person belongs to this clique. Actually, that concept is coming from here. This is the smallest meaningful clique. It is also known as a complete graph, shows each node connected to every node. So my question to you is, why is this structure important? Why is this structure specifically important in real life and in graph theory? It is known as a clique, and it's also known as a complete graph. Anyone? So think of these 3 nodes as 3 people. If there are 3 people, what does it mean? A knows B, B knows C, C knows A. That means everyone in the group knows each other. That is why it is called a clique. So when you refer to a group of friends who interact among themselves, you call them a clique. Right? Why do you call them a clique? Because they are very close to each other. They interact with only themselves. They don't interact with the outside world very much. So there may be different cliques for different things. So the notion of cliques is important because it's the strongest relationship you can find in a graph. Every person or every entity is connected to every other entity. But if I remove one of these edges, it is not a clique. Why? A knows B, B knows C, but C doesn't know A. In order for it to be clique, it has to be very strong. I am emphasizing this because we will use this for the notion of community later. Hyperedges, as I mentioned, connect more than 2 nodes. We have not discussed that. The notion of a community approximates a clique and is used quite extensively in aggregate analysis. So first you need to understand what a clique is, and certainly you need to understand what a community is if you want to do any kind of aggregate analysis. So for connected graphs with n nodes, how many edges are possible? If I have a graph with n nodes, what is the maximum number of edges possible? To understand it, so here is a graph of 3 nodes. The maximum number of edges for 3 nodes is 3. If you take, yesterday there was a board here, today it's gone, otherwise I would have written it, but that's right. So if you take a graph of 4 nodes, how many edges can you draw? I can't hear you.
4 edges would be formed.
4 nodes, how many is the maximum number of edges?
6.
6. Somebody said 6, right? 4 plus 2. So you have to be careful. So the question is, how do you generalize it? If you have n nodes, how many edges can you have undirected? n into n minus 1 by 2. That is what a complete graph is. There is also the notion of sparse graphs that have very fewer edges. Linear graphs also have linear means the nodes are connected one to each other. So connected and disconnected graphs. So if you have a set of disconnected graphs, then it is called a forest. Typically, vertexes are numbered uniquely for analysis purposes. Most packages expect it to start from 1. Why? It is important to understand because sometimes the data set may or may not start from 1, but if you want to do the analysis, you have to renumber them to start from 1 and then you have to map them, otherwise the package will not give you the correct results. You can also have labels. This is very important, we'll come to that. So in the transactional model, there are no question of labels, right? There are attributes and values, columns and values. But in a graph, I can have a label for the node. I can say this node represents a person, this node represents a faculty, this node represents an animal, this node represents a building. So I can have different labels for nodes. Similarly, I can also have different labels for relationships, edges. It may be a friendship relation, it may be a connection relation, it may be a follows relation, it may be a greater than relation. So there are large number of relationships that you can express, large number of node types that you can have. And you can have multiple nodes. So you can also have labels for nodes and edges. You can have multiple labels as well as for nodes and edges. So Freebase is a knowledge graph. If you are familiar with it, you can look it up. You can also associate weights. This is very important. When you draw a graph, typically we draw a graph without anything, but if you draw a graph of a road transportation network and you are connecting two cities, you can put the distance as the weight, right? Because that is useful if you want to compute the smallest distance connectivity for cities. You need to make, it's not enough if you have a path. One path may be larger, one path may be smaller, so you need to take into account the distance between the cities. So different problems need different features for accurate modeling analysis. So graph-based data model, graph is an intuitive and obvious choice for data sets that have structural information, meaning relationships. Graphs can be used to accurately model and represent many diverse data sets. Graphs are suitable for capturing arbitrary relationship. It doesn't matter what relationship it is. The graph is still a graph, but the labels will be different. Node labels will be different, edge labels will be different, node weights will be different, edge weights will be different. Graphs are suitable for capturing arbitrary between various objects. Graph-based mining analysis aims at discovering communities. We just discussed the notion of clique and their approximation. Centrality nodes, we will come to that. Interesting and repetitive patterns, this is known as substructure or motifs. Temporal evolution of events. So you may want to know how things have changed over the period. So if a telephone company has a snapshot of a graph of their customers and their calls up to this point, then they can have another graph for the next 3 years. Now there is a difference between these two graphs. Some connectivity might have been gone here, new connectivity might have established. You want to analyze the difference between them, how things are changing. So what are the application domains? So this is the basis why we are looking at it. Chemical reaction chains, computer-aided design circuit analysis. You know, computer-aided design circuit is essentially a graph. Layout is a graph. And you need to make sure it's planar. It's a planar graph. You cannot have crossovers. Social networks, credit domains, web analysis, games. Most of the games, whether it's tic-tac-toe or chess or any of them, are modeled as graphs. and the movement are also models of from which node can you reach which other node. Program source, this is very popular. So when you write a program, there is a whole theory of program profile and program analysis. So how do you analyze a program? So you can convert it into a graph based upon the flow of execution. Character recognition, Chinese characters and other characters, geology, web and social networks, friends in Facebook, follows in Twitter, connected in LinkedIn. So how do we map a real world problem to a graph? So these are the things that are used. Any object or an entity is represented as a node or a vertex. Object's attributes is a vertex label. So if you have a person's height, weight, eye color, whatever it is, can become labels for that node. And it will be unique for each person. The labels will be different for each person. Relations is represented as edges between objects. Type of relation is an edge label. Now for analysis from this graph, you have the notion of a substructure. What is a substructure? We'll see it maybe if not today, tomorrow. Connected subgraph. It's a smaller, remember I talked about the benzene rings, small substructures that repeat many times. That's a substructure. And the reason, this is also true in DNA, G, T, A, C and other things, they keep repeating. There is the difference between a substructure and its instance, a specific instance of the substructure, the notion of a community group of nodes that are strongly connected. It doesn't say completely connected. So remember that. It's not completely connected, but it is strongly connected. There is a difference between that. Then there is this notion of centrality, hubs, betweenness, closeness, eigenvector. If you count the number of frequent substructures, then it becomes counting substructures. So now what are the different types of graphs we use for modeling? The first one is what we saw, the notion of a simple graph, also known as a network on a monoplex. Nodes are entities, single edges between nodes, weighted or unweighted, single or combination of feature-based relationship. Algorithms exist for shortest paths, spanning tree, finding cycles, communities have subgraph mining, frequent subgraph counting, and so on. So this is a simple graph, does not have loops. Then we have the notion of what is known as attributed graphs. So what is the difference between a simple graph and an attributed graph? Still, nodes are entities, they can have labels, but you can have multiple edges between same nodes. So another example that you guys can understand is, if there are two people and both of them are on Facebook and on LinkedIn and on Twitter, then they have three relationships. One for the Facebook, one for the LinkedIn, one for the Twitter. These are different relationships, right? One is friends, one is connected, one is follows. Semantically, they are not the same. So if you want to represent multiple relationships between the same nodes, you cannot do it with this. You have to do with this. So multiple edges, edge labels. But the problem with this type is there are not many algorithms for that because it's a complicated data structure. Suppose say you have an attributed graph and there are 5 different relationships. If you want to analyze only one relationship in that graph, how do you do that? You have to separate that graph into a simple graph and then analyze that. You want to analyze a different relationship, you have to do the same thing. Third relationship, you have to do the same thing. You cannot run the algorithm on an entire graph, and it is difficult to say only analyze this relationship. Usually graphs with specific features need to be separated for analysis. So, traditional approach, so how can we use this for modeling? So here are single edge monoplex. These are the entity nodes. These are the relationship edges. Weights can be used for strength. Direction can also be added. This is a very widely used relationship. As I said, friend graph follows graph, World Wide Web graph, road networks in Google Maps, power grid networks, identifying critical node junctions. All of them can be modeled using a simple graph. And we do. And it's very easy to do so. For an attributed graph, as I said, the same entity may take different incarnations or avatars. So you may have entities of type red, you may have entities of type black, and you may have entities of type blue. So they are different. You have buildings, you have persons, you have animals, whatever it is, chairs. You can also have different relationships. Relationships across black nodes, relationships across blue nodes, relationships across red nodes. So multiple entities can be represented. Here is an example: actors, directors, movies, distribution houses. So multiple relationships can be represented. Acts in a movie, co-acts, directs a movie, distributes a movie. So there can be multiple edges between the nodes. You can see that this graph is complicated and the analysis also is more complicated, but it is more expressive. It can model things that the previous one could not model. Previous one could not model multiple relationships, multiple types of nodes, but this one can model it, but analysis is a different issue. Any questions? No? Okay. So you can see how this graph is quite different from the previous one. So, multi-edge monoplex may include labels. Processing is difficult. Graphs of different colors need to be separated or converted, combined into a simple graph. And during that process, information may be lost. If you just say all nodes are similar, then there is some loss of information. Okay. So here is a sort of a what we call a back of the envelope comparison of various features: modeling clarity, aggregate analysis flexibility, computational efficiency, drill down and visualization for these two types of graphs. So modeling clarity, it doesn't support a lot of things, multiple relationships. Aggregate analysis flexibility to some extent because you can do subgraph counting. Computational efficiency depends on the computation being performed. Different algorithms have different computational complexity, and drill down and visualization is possible. When you come to attributed graphs, the modeling clarity is better than this one. Aggregate analysis flexibility is typically not available except for subgraph mining. Computational efficiency, there is overhead for separating the graphs into multiple graphs for processing, and drill down is possible. I'll come to this later. So if I can assume that you have a decent understanding of what a graph is, why we need a graph for modeling real world problems, why this modeling cannot be done using previous representations we had, then we need to dive a little bit more into understanding various graph properties. So there is this notion of graph density. It represents the ratio between the edges present in the graph to the maximum number of edges that graph can contain. So if I have 3 nodes, just to take a small example, if I have 3 nodes, I know that the maximum number of edges is 3. But if the graph has only 2 edges, then the density is 2 over 3. If it has only 1 edge, then it is 1 over 3. Similarly, for a 4-node graph, maximum number of edges is 6, but the graph may have only 3 edges, then the density is 0.5. So the maximum density is how much? 1. If every node is connected to every node, then it has a density of maximum number of edges in the graph, maximum number of edges possible. This is also the clique. A clique has a density of 1. But most of the graphs we deal with are what are known as sparse graphs, meaning you might have heard of sparse matrix, right? In the matrix, if lot of elements are 0, we call it a sparse matrix. In the same way, if number of edges are small or less, we call it a sparse graph. So density is 1 for complete graph or a clique. Given the number of nodes, you can compute the maximum number of edges. We gave the formula earlier, you use that. The density is a measure of how many relationships exist compared to the maximum. So this is useful. This is one of the graph characteristics. The more dense a graph is, the more computation you need because more edges you have to deal with. Nodes are the same. Here, density is purely based on the number of edges for the same number of nodes. Remember, for a directed graph, the number of edges possible is twice the number of 1 because you can have 1 this way, 1 this way. Sparse and dense graph, there is no defined threshold for this. So the threshold, if it is 0.1, if the density is 0.1, it's a sparse graph. You can assume if the density is less than 0.5, it is a sparse graph. If the density is greater than 0.5. So whatever threshold you use, you can use it. So, another property, distance between 2 vertices. This is defined as the shortest path between vertex A and vertex B. You take a graph and you take two vertices. Remember, there can be multiple paths, right, between the same 2 vertices. But the number of edges between those vertices need not be the same. So that is why we have this shortest path, meaning the less number of edges between the 2 points. Less number of vertices between the 2 points. If you take if you take a graph of 4 nodes, you have 2 edges crossing each other node. So between A and B, you have 1 edge, but you can also go from here to here to here. That is 2 edges. That is not the shortest path. Then there is the notion of eccentricity of a vertex, maximum distance from a vertex to all other vertices in the graph. So you take a vertex and compute its shortest distance to every other node. And the maximum value is the eccentricity. Then there is the notion of the radius of a graph. The minimum value of eccentricity from all vertices is considered as the radius of the graph. So again, if you understand it, if you want to understand it, play with small samples, small examples. Makes it clear. Rather than just looking at the definition, take a small graph and see what the diameter is. Add another edge to the graph and see what the diameter changes. Same thing. So it's always important to play with it with small examples to understand the concept very clearly. I certainly encourage you to do that. So if you have a radius, you have a diameter. This is the minimum value. is the maximum value. Makes sense, right? Minimum value is the radius, the maximum value is the diameter of the graph. Central point and center. Again, you can visualize these things. What do you think is the central point? A point in a graph which is more or less located at the center, right? What does it mean? Means its distance to any node is less. To all the nodes is less, right? If you take a point on the edge, it has a long distance to other nodes. If you take a point in the center, it doesn't have. So the vertex having the minimum eccentricity is considered as the central point of the graph. So it has the minimum distance to any point in the graph. So take a vertex and see which vertex has the minimum distance to any point. So again, the computation is not easy, right? Because you have to do it for all vertices and compute the distance for all other vertices. So this is a complex computation problem. You can do it for 5 nodes, but doing it for 500 nodes is very difficult. And the set of all central point is considered center. Why the set? Because there may be many nodes with the same value. Then that becomes the center of the graph. So typically the center of the graph will be what it means, and the definition corresponds to it. So this is a theorem. I just put it in order to give you an intuitive understanding of, if you have a graph, V vertices and E edges is a non-directed graph with vertex V equal to n vertices, then sum of degree Vi is equal to 2 times the number of edges. Now, a lot of these things you should be able to understand intuitively, right? What is the degree of a node? I should have put that earlier, perhaps it comes a little bit later. The degree of a node is the number of edges incident on that. In that triangle graph, every node has degree 2. But if you take a square graph, 4 nodes, some nodes have degree 3, some nodes have degree 2. But this theorem is correct. If you add up all the degrees of all the nodes, that should be the same as twice the number of edges. Why is that? I mean, this can be understood intuitively. Proof is a different thing. Think about it. If you take an edge, it connects 2 nodes. That means it contributes to the degree of this node, it contributes to the degree of this node. That means every edge contributes to the degree twice. So 2 times the number of edges. If you think about it intuitively, it's very easy to understand. Derive the above for directed graphs. Girth. Girth is like the circumference. The number of edges in the shortest cycle of G is called the girth. Then we have the notion of connected graphs. This is important to understand. A graph is connected if every pair of vertices in the graph is connected. That means there should be a path from every vertex to every other vertex. Otherwise, it is not a connected graph. So if you take an isolated node or 2 graphs, then this is a connected component, connected graph, this is a connected graph, but there is no path between these 2. That means there is a path between every pair of vertices. An undirected graph that is connected is called, that is not connected is called disconnected. An undirected graph G is therefore disconnected if there exist 2 vertices in G, that no path in G has these vertices as endpoints. A graph with just 1 vertex is considered by definition connected. An edgeless graph with 2 or more vertices is considered disconnected. So these are the definitions. A connected component. So so a connected component means if you are given a graph, you may have multiple connected components, and that is also called a forest. So a connected component is the maximum connected subgraph of an undirected graph. Each vertex belongs to exactly one connected component, as that each edge. A graph is connected if and only if it has exactly one connected component. So if there is only one connected component, then the entire graph is connected. Then there is the notion of bipartite graphs. Have you heard of bipartite graphs? How many of you go on Tinder or any of those things? How many of you go? You may want to disclose that, but I'm sure you are familiar with Tinder, if not with bipartite graph. What does Tinder use? Bipartite graph. Males are one set of vertices, females are another set of vertices, and they try to match. That's a bipartite graph. So a bipartite graph is a graph whose vertices can be divided into two disjoint and independent sets U and V. In Tinder, it's male and female, or maybe more categories nowadays, such that every edge connects a vertex in U to one in V. Vertex at U, V are usually called the parts of the graph. Equivalently, a bipartite graph is a graph that does not contain any odd length cycle. So that's a theorem mathematicians love, and they have proved it. You don't have to worry about it. So the important thing is cardinality of U and V need not be the same. We do not assume the same number of people on this side, the same number of people on this side. In a complete bipartite graph, so you can also have a complete bipartite graph, every node, each node in U have edges to all the nodes in V. A graph that can be colored using two colors is a bipartite graph. Every tree is bipartite. Is every bipartite. So I put some of the, these are slides from some of the courses I've been teaching. So you'll see the homework problems. You can try it if you like. So let's understand. So is this a bipartite graph? Which means that you should be able to identify two sets of vertices, set A, set B, and edges between those two vertices. So this is an illustration to show that the topology of a graph can be very misleading. Just by looking at the topology, you cannot conclude a lot of things. If I redraw this graph in this way, then it becomes more clear that it is a bipartite graph. Because 1, 3, 5, 7 is one set, 2, 4, 6, 8 is another set, and the edges only exist between this set and this set. There are no edges between these sets, there are no edges between these sets. This graph is the same as this graph. No difference. But the topology can make a difference in how we understand a graph. So this is very important to understand for isomorphism, for subgraph isomorphism, and it makes a difference. Does everyone understand this? So it is, just convince yourself that all these edges exist in this graph in the same way. There is no edge between 1 and 3. There is no edge between 1 and 3. There is no edge between 3 and 5. There is no edge between 3 and 5. So number of edges in this graph is the same as the number of edges between the same nodes. Number of nodes are same, but this is easy to understand as a bipartite graph. Are these two graphs isomorphic? I think I already gave you the answer. These two graphs are exactly the same. There is no difference between them. Now, one of the difficult problems in graph theory or graph is, if you are given these two graphs, can you figure out computationally that they are the same? And that is not easy. So we have done, we use bipartite graphs, and it's also used for max flow. So all of the max flow algorithms use the bipartite graph and other graph capability, source and sink and other things. So there are different ways of computing what we call the maximum weight match. So given these set of vertices and these set of vertices and the edges between them, you need to pair. That's why. So this is what I was telling you. If you understand Tinder better than bipartite graph, which I think you do, you can think of this as one group of people, another group, and these numbers as likings or how they match with each other. So remember in Tinder or Make Your Match, Shadi.com, I don't know what it is, they have a list of properties, 20 different characteristics, and you take, I like this, I like this, I like this, I like this, then they take the same list from the other person and match. When they match, they derive a weight. What is the likelihood of this person matching this person? And that's how this graph is formulated. That's what happens behind what you may be using for without understanding what it is. You only know how to swipe left and swipe right, but you don't know anything else. So there are different ways of computing or matching. One is the maximum weight match. This is in this color, so that is A to Y, B to C, 15 plus 5, 20. So this is one way of matching. So it's kind of maximum match. That means A should be paired with Y, B should be paired with C. There are other ways of doing maximum number of pairings with maximum weight. I don't know, I added a couple of things that's not come there. MWPM, MWRM. So there are different ways in which you can do this matching, and all of them have some meaning or semantics or relationship that is appropriate for what you want to do. Okay, so let me just do this planar graphs and stop and then break. So what is a planar graph? You should also know this. You guys drive, you guys travel. So if you travel, you should understand what a planar graph is. So can you tell me when the road network is not planar? So a planar graph means you should be able to represent it in 2 dimensions. That is what a plane is. A plane is x coordinates, y coordinates. So can you give me an example of a road network that you know very well that is not planar?
So when there is an overhead bridge,
Huh?
when there is an overhead bridge that we need to cross.
A bridge. That is a planar thing. If the bridge is not there, those 2 roads will have to meet. And if they meet, that is a point that creates a bottleneck. So all our road networks are non-planar graphs. If you only use planar graph, traffic will be disastrous. Right? So a planar graph is a graph that can be embedded in a plane, 2-dimensional plane. It can be drawn on the plane such way that the edges intersect only at endpoints, and this is known as the planar embedding. So for example, this is a planar graph. This is a planar graph. Is this a planar graph? He's shaking his head. Is it yes or no? Well, it turns out it is not. So this is known as the utility graph. These 2 are planar graphs. Try drawing this. Try drawing this without an edge crossing another edge. That is the test. If you, in all of these, an edge does not cross the other edge because it ends here. But if you can draw this where you don't cross over another edge, that crossover is your bridge, is your flyover. And you can see that this, although looks like a non-planar graph, it is a planar graph. This can be written in this way. It has 6 edges, this has 6 edges. This looks like this edge is crossing over here, but here it is not. And these two have been proved to be the smallest non-planar graphs, K5 and K33, have been shown to be, both have been shown to be non-planar, shown in the sense not just by drawing, but proving. So, in general, okay, so let us stop here on this note and then continue after break. Okay, good afternoon. So let's continue with this one. So, in general, graph algorithms require a systematic way of exploring a graph. The most important and common technique is two algorithms, depth first search and breadth first search. You might have heard about it, you might have studied that. I'm going to give just a brief understanding of it. Several algorithms have been produced for planarity testing, and these guys, Hopcroft and Tarjan, were the first to show that planarity testing can be done in linear time. So this is a big thing. If you can do something in linear time, that is the best. You cannot do much better than that. A finite graph is planar if and only if it does not contain K5 or K33 as a minor, and this is K5 and this is K33. Any graph that contains this smallest non-planar subgraphs is non-planar. That's all it is. So, graph properties and algorithms have been developed over a long period of time. So the difference is mathematicians concentrated on graph properties, proving graph properties, Hamiltonian cycles, subgraph S1, coloring problems. Focus was on complexity, feasibility, not on the size and mechanical computation. I think this is what you need to understand, what was being done earlier theoretically and what is being done now computationally. So they did not have access to the powerful machines, so they could not go beyond small problems, but they have done a lot of work which we are still relying on using. What we are now doing is to develop more efficient algorithms for the same things they have done. So with the advent of computers, modeling using graphs and computation on graphs was useful to solve real-world problems, shortest paths, minimum weight spanning tree, hubs, communities, etc. So this is just a snapshot of various algorithms like breadth first search, depth first search, topological sort, minimum spanning tree, prim algorithm, and other things with time complexity, space complexity, application, and other things. So to summarize, a very powerful data structure. Graphs are very powerful data structure for modeling and for analysis. It is not enough if you can model something to be amenable to analysis. Take for example, relational model. If you model an application as a relational database, and if you cannot query it, what is the purpose of that? So SQL, which is which has a foundation in set theory, has been very useful because you can write powerful queries and embedded algorithms using that. So that's very important. Many aggregate algorithms can be used to infer knowledge from this representation. As the graph sizes increase, parallel processing approaches become more important. For this, algorithms need to work on parts. So this is another thing. If you have a traditional data, it's easy to partition them. But partitioning a graph is not easy. I mean, partitioning itself is not difficult. But when you partition a graph, you lose information. Because remember, some edges belong to one partition, nodes belong, and another end of the edge belong to the other partition. What do you do with those edges? If you don't keep those edges, you lose information. So you cannot just partition a graph in whatever way you want, because you won't get correct results when you process the partitions and put them together. So this poses an additional problem for graph partitioning. For this, potential information loss due to partitioning need to be handled correctly, requires a lot of bookkeeping and other techniques, or approximate solutions can be obtained. So this leads us to graph mining and analysis. We have seen this earlier, so I'm going to wrap this up and go to the next set of slides. We need to start lecture 7.